Hello everyone, welcome to the session 5 of module 2. So in the previous session we have covered the first algorithm, that is first come first served scheduling. So in this session we'll try to complete SJF scheduling, SRTF scheduling. So in this algorithm, that is for each and every process there will be a value that is called as a CPU burst which is assigned to that. So if two or more processes or two processes have the same length of a CPU burst, so in order to break the tie between these the process, we use first come first schedule method. But here there is another term that is more appropriate for this algorithm is a shortest next CPU burst algorithm. Why? Because see, this scheduling depends upon the length of the next CPU burst of a process rather than depending upon the total length. Hence it is called as shortest next CPU burst algorithm. Or this is an optimal algorithm where it gives a minimal waiting time, that is a minimal average waiting time for a given set of process. So here one important thing that you need to understand that moving a short process before a bigger process or a longer process, that will decreases the waiting time of the shorter process than it increases the waiting time of the long process. So obviously the average waiting time will be decreased. So these are the important points. But here there is one difficulty with the SJF algorithm, that is we need to identify or knowing what is the length of the next CPU request. So this is the one of the difficult thing with respect to SJF. So when you have a long-term scheduling in a batch system, we can give the length, the process time limit, where the user will specify what is the length of the process time during the submission of the job. So that is one way to get out from this difficulty. But as you know, this SJF algorithm is optimal, where it cannot be implemented at the level of short-term scheduling method, because one way, that is there is a difficulties, that is there is no way to know what will be the length of the next CPU burst. But there are some different approaches are there where you can approximate these values. That is, you may not know the length of the next CPU burst, but you can predict what could be the value of its, that is value of next CPU burst. So this is the basic information regarding the shortest job burst. We have seen that advantage, that is SJF is an optimal and it gives the minimal average waiting time for a given set of process. Why it is, we have discussed. And what is the major disadvantage here? Determining the length of the next CPU burst is the difficulty. In this SJF algorithm, there are two variants are there. One is with respect to non-preemptive SJF and another is preemptive SJF. When we call it as a non-preemptive SJF, that is, you know that once the CPU is given to the process, until that process completes its execution or terminated, the CPU will not be given back. The similar thing is with respect to non-preemptive SJF, where the current process is allowed, that is whatever the process which is currently executing, that process will be allowed to finish its CPU burst, even though any other process which is having a shortest remaining time or shortest burst time, the process will not be terminated. This is with non-preemptive. But the condition with respect to non-preemptive is, assume that if any new process has the shortest CPU burst, then whatever it is executing currently, that process is stopped and the CPU is given to the other process which is having the shortest CPU burst. Hence it is called as shortest remaining time first scheduling. So this is the basic information with respect to this algorithm. We shall see how we can solve the problem with respect to this scheduling. Now let's see the problem with respect to non-preemptive SJF. See here, you have a set of process and also the length of the CPU burst time, which is given here, and the units is millisecond. So what actually you need to identify? Two things. One is to draw the Gantt chart, and also you need to identify what is the waiting time for individual process and also the waiting time, that is average waiting time for this entire set of process. So we'll start with the Gantt chart. So as you know that here there is no information regarding the arrival of the process, means no arrival time has been given. Only you have the process and also the burst time. When these only two information is given, now you can choose whichever the process is having the lowest CPU burst time. So when it comes for this set of process, the first thing is P for having the smallest burst time. So I can write, means I can give the, means this process is executed first because it is having smallest CPU burst cycle. So it starts with a 0th millisecond and it ends with 3. As it is said that it is non-preemptive, which means that until the process completes, the CPU is not given to the other process. So the next is, which is having the smallest burst time, is P1. So P1 is executed for 6 more milliseconds. So P1 here, and the value is 9. And the next one is 7, P3, which is executed till 16 milliseconds. And the last one is P2, which is having 8 milliseconds of a burst time. So that is P2 here and 24. Now you can see what is the waiting time for individual process. P1 is 3, P2 is 16, P3 is 9, and P4 is 0. And what is the average waiting time here? 3 plus 16 plus 9 plus 0 divided by 4 is equals to 7 milliseconds. Let's consider the example with respect to the shortest job first scheduling. So here the statement is you need to consider the following set of process with the length of CPU burst, which is given in millisecond. And also you can see here there are 5 processes are there. Along with that there is arrival time and also burst time. So what actually you need to identify? You need to draw the Gantt chart showing the execution of the process using SJF, and also what is the turnaround time of each and every individual process, and also you need to calculate the average waiting time. Let's see how to solve this problem. So let's start with the problem. First we shall draw the Gantt chart. That is what actually we wanted to identify. The first thing. So when you see the processes here, 2 processes has arrived at the same time, that is P1 and P2 at 0th second, and you can see here the burst time is given as a 10 and 1. You need to pick the process which is having the shortest burst time. So what I do, I start with the process P2 for executing from 0th second till it completes, because it is shortest job and it is non-preemptive. So I complete the execution with the P2. So as soon as I complete P1, in the ready queue, you can see here, ready queue, P1 has already arrived. And you can also see that when it completes 1 second, that is P1 completes 1 second, no other process has arrived till now. So what best we can do is, I can pick the process from the ready queue, that is P1, and give the CPU to the P1 so that it will start it executing. Until it executes, it will not give the CPU back. So what is the, how many seconds it will execute? How many milliseconds? It will execute for 10 burst time. So 11 here, it is 1 and it is 10 here. So meanwhile, all the process process P1 completes its execution. Remaining process has arrived and they are waiting in the ready queue. Which are those? P3 has arrived and also P4 has arrived at 5th millisecond and P5 has arrived at 10th millisecond. So you can see here, after completion of P1, now P3 is waiting for its execution, P4 is also waiting for its execution, and P5. But actually what you need to do, you need to pick the process which is having the shortest job. So what I do, I pick the process P1 because it is having the shortest burst time, that is 1. So I pick that and I take it from this one, P4, and I will execute that for 1 second. And after that, which is having the shortest? P3. P3 is having 2 burst time, and I take this here, you can see it is 14. And the last one is P5, which is having 5 burst time. So P5 here, you can write it as 19. So this is how we write the giant chart. This is one thing. Second one is, you can also need to calculate with these values. What is the completion time? See, it is nothing but completion time. Completion time for P1 it is 11, P2 it is 1, P3 you can see here it is P3 it is actually. So P3 here it is 14, P4 it is 12, and P5 it is 19. So completion time is done. So now what is the turnaround time? How do you calculate the turnaround time? CT minus AT. So 11 minus 0, sorry, it is 11, and 1 minus 0, 1, 14 minus 3, 11, 12 minus 5, 7, and 19 minus 10, 9. Now we shall see what could be the waiting time for this process. So you know the formula, turnaround time minus burst time. So for process P1, turnaround time is 11 minus burst time is 10, the remaining is 1. So now next it is 1 minus 1, 0, 11 minus 2, it is 9, 7 minus 1, it is 6, and 9 minus 5, it is 4. So now what is the average turnaround time? It is 11 plus 1 plus 11 plus 7 plus 9 divided by 5. The value will be 13.9 divided by 5, it is 7.8 millisecond. This is with respect to turnaround time. Then what is your average waiting time? Now it is 1 plus 0 plus 9 plus 6 plus 4, it is 20 divided by 5, now it is 4 millisecond. So this is how we solve the problem with respect to shortest job first scheduling. Now let's consider another type of problem with respect to the SJF, that is preemptive SJF, and it can also be called as SRTF. So the process and also arrival time and the burst time is given. We need to identify what is the turnaround time and also waiting time for individual process and also the average of this process. So in this problem, you can see process P1 has arrived at 0th millisecond and no other process has arrived till now. So what I do, CPU is given to the process P1 and it will execute for 1 millisecond, and once I execute, I will check whether any other process has arrived with the shortest burst time than P1. So here you can see P1 has executed for 1 second and remaining is 7 milliseconds yet to execute that. So at first millisecond, P2 has arrived with the burst time is 4. So now P2 and P1 has compared. So which one is having the shortest remaining time? That is P2. So what I do, I give the CPU to the process 2 and I will execute for 1 second and I check once again when any other process has arrived at 2 millisecond. So you can see here P3 has arrived and what is the burst time here? 9. So currently P2 has executed for 1 and remaining is 3. Now P3 you can check here the burst time is 9. So I compare P1, P2 and P3. Among these three, P2 is having the shortest remaining time. So what I do, I execute one more millisecond. So here it is 3 and minus 1, it is 2. And as soon as 3 milliseconds are completed with this P2, I check once again when any other process has arrived at 3rd millisecond. So P4 has arrived and the burst time is 5. So right now all the process has arrived and you can check that among 4 processes the remaining shortest remaining time is P2. How much time it is left with? 2 milliseconds. So what I do, I make P2 to execute for 2 more milliseconds. So you can see that 5 here. So you know to write this one 5. So directly I have written P1 after P1. P2 has executed for 4 milliseconds and it is completed its execution. So right now P2 is done. And among these 3 processes, that is P1, P3 and P4, which is having the shortest remaining time, that is P4. Again I check P4 is executed for 1 second and I check any other process has arrived. No, right now no other process are there in the ready queue. So you can check it out. If I execute for 1 second, the remaining is 4. So again I compare with the P3, P4 and P1. P4 is shortest. Again I execute for 1 second and remaining is 3. Again I compare. So means this process will continue. So when I do all those things, at last I receive P3 will be the shortest compared to all other processes, that is P1, P3 and P4. So what I do, I complete P4's execution burst time. What is the burst time here? 5, that is 10 I have written, and the remaining is P3 and P1. P1 having shortest remaining time than P3. So I execute P1 for 7 milliseconds and it is 17. And the last one is, you can see here, that is P3, which is having 9, that is it is 26. So this is the way how we go with the shortest remaining time pass, that is preemptive SJF. So how do you calculate the completion time here? P1 has completed its execution when it is completed at 17th millisecond. So 17. P2 has completed at 5th millisecond and P3 has completed at 26 and P4 which is completed at 10th millisecond. The turnaround time here, you know the formula here, CT minus AT, that is completion time minus arrival time, and waiting time is turnaround time minus burst time. So 17 minus 0, 17, 5 minus 1, 4, 26 minus 2, 24, and 10 minus 3, 7. This is the turnaround time for individual process. What about the waiting time? That is 17 minus 8. It is 9, and 4 minus 4, 0, and 24 minus 9, 15, and 7 minus 5, 2. So this is the turnaround time and also the waiting time for individual process, and the average time you can calculate that. This is average waiting time. So what is the thing? 9 plus 0 plus 15 plus 2 divided by 4 will get the value. Is 26 divided by 4 is equals to 6.5 millisecond. That is average waiting time. Similarly for turnaround time, that is 52 divided by 4, you will get 13 millisecond for average turnaround time. So this is how we solve this problem. I hope you have understood this problem. So we'll start with this drain chart. So process P1 and P2 has arrived at the same time. Let's consider another problem. Here there are 5 processes are there. Arrival time and burst time is also given. So what you need to do, you need to write the drain chart using SRTF, and you need to find the turnaround time and also the average waiting time. Let's see that. So according to this algorithm, I need to pick which is having the shortest remaining time. So P2, I execute it for 1 millisecond. So after that, I check once again if any other process has arrived at first millisecond. So right now here no other process has arrived. Whatever the process which are in the ready queue is P1. So P1, I pick that and I check any other process has arrived. So at 2 millisecond no other process has arrived, so I will continue for 1 more second and I check here, and again I check any other process has arrived. So process P3 has arrived at time, arrival time is 3 and burst time is 2. So right now P2 with 1 millisecond is completed, the remaining time is 0, and P1 it has 10. So right now I have executed 2 milliseconds, so the remaining time is 8. So at the 3rd millisecond process P3 has arrived. What is the burst time? Is 2. So now I compare P2, P3 and P1. P3 having shortest time. So what I do, whatever the process, whatever the CPU has been assigned to P1, that is taken back from P1 and given to the P3. So what I do, P3. So now P3 will execute for 1 second and check whether any other process has arrived. So at 4th millisecond no other process has arrived. So again it is compared with P1 and P3. P3 is having shortest remaining, so I execute for 1 more second. So 5th millisecond. So at 5th millisecond P4 has arrived. What is the burst time? Here is 1, and here you can see we had only 2 milliseconds of burst time with P3 and I executed it completely. So the remaining time is 0. So P2 and P3 are completed now. So as soon as I'm done with P3 execution at 50 millisecond, P4 has arrived with 1 burst time. So I compare P4 and P1, which is having shortest, P4 having the shortest. What I do, I execute it for 1 millisecond. So now it is 6. So P1 have only 1 millisecond of burst time, so it is completed. Now, the only one process which is there in the ready queue, that is P1. So the next process will arrive at 10th millisecond. Until then, I can execute, that is P1 can execute. For how many seconds? For 4 milliseconds. So P1 is executed for 4 milliseconds, that is 10 here. So 4 millisecond here, and remaining is 4. And at 10th millisecond, P5 has arrived. What is the burst time here? 5. Now P5 and P1 is compared. Which is having shortest? P1 is having shortest. So the P1 is allowed to complete its execution. So here I can write 14 here. So P1 has completed its entire burst time and it is completed at 14 milliseconds. And the only one process which is waiting for its execution, and the last process is P5. What is the burst time here? 5, and it is executed completely, and this is 9 here. So this is the way how do we write the giant chart with respect to this one. And here you can erase this, all the things. This is for just for understanding purpose. You can remove this one. This is the way how we write. And what is the completion time here? Here you can see with respect to the P1, what is the completion time? It is 14, P2 1, P3 5, P4 6, and P5 it is 19. Turnaround time, as usual, you know, CT minus AT. What are the values are? It is 14, 1, 2, 1 and 9, and the average waiting time, that is for turnaround time, it is 27 divided by 5 is equals to 5.4 millisecond. This is done. What are the waiting time here? The waiting time is turnaround time minus burst time. Here 14 minus 10, it is 4, 1 minus 1, 0, 2 minus 2, 0, 1 minus 1, 0, and 9 minus 5, it is 4, and the value is 8 divided by 5 is equals to 1.6 millisecond. This is with respect to the waiting time. So these are the problems with respect to the shortest remaining time. First we shall see with the next algorithm. The next algorithm is with respect to priority scheduling. You can observe here in this algorithm a priority value which is associated with each process, and the CPU is allocated to the process with the highest priority. Assume that if two processes or more than two processes are having equal priority values, and to break the tie between these processes, a method called as first come first serve method has been used to break the ties between the process. The important thing is the priorities can be defined either internally or externally. So let's see that what actually how these priorities can be defined with respect to the internally. See, priorities with respect to the internal that uses some of the measurable quantities for computing the priorities of the process. For example, the time limit of the process, the memory requirement of that process, and the number of open files, and the ratio of average IO burst to the average CPU burst that have been used in the computing the priorities. This is internally, right? When we have the external, see, these are the priorities which are set by the outside the operating system. So such as means which of the process that are more important, and what type and what amount of funds being paid for that computer use, and some of the political factors that influence on the external priority. So these are the factors which actually influences the priorities of a process. Now the priority scheduling can be either a preemptive or a non-preemptive. What do you mean by preemptive? So if the CPU is executing a process, if any other process which is having higher priority than whatever it is currently executing, the CPU is taken from that currently executing process and given to the higher priority process. So this is with respect to preemptive. And non-preemptive in the sense, until unless the process completes its execution, the CPU will not be given to the other process which is having the higher priority than what it is currently executing. This is non-preemptive. So what is the advantage here with respect to the priority scheduling? That is, one of the major thing is the process which is having the higher priority process can be executed first. So this is one of the advantage. But here the major problem with the priority scheduling algorithm is, we can say that it is indefinite blocking or starvation. So when we call that indefinite blocking or starvation, that is, if a process that is ready to run but it is waiting for the CPU, that can be considered block. That is, remember, the process or the priority scheduling algorithm that will leave some lower priority process waiting indefinitely. So this is the one of the major problem with the priority scheduling. What is the solution for this one? The solution for indefinite blocking is a method called as aging. That is, it is a technique that gradually increases the priority of the process that waits in the system for a longer time. So this is the solution for indefinite blocking or starvation with respect to priority scheduling. So now we shall discuss with the problems of priority scheduling, that is with preemptive and also non-preemptive. So in this example, there are 5 processes are there, and we need to assume that all the 5 processes have arrived at time 0. So in the order, that is P1, P2, P3, P4 and P5, and the length of the CPU burst time which is given in milliseconds. You have to solve using a non-preemptive method. And one more thing is, here the priority value, they have not mentioned clearly that lower the priority value, highest the value, or highest the priority value, the lowest the value. So in the sense, if they have not given any conditions like this, so what you need to do is a smaller priority value, you need to consider that as highest priority. So in this problem, process P2 is having smaller value. It means that it is having highest priority than any other process. Next is P5, next is P1, next P3, and the last one is P4. So now you have to execute according to this priority values irrespective of the burst time. So I start with 0 second, and P2 will be executed, and it is non-preemptive, so the P2 will execute completely. What is the burst time here? 1. So 1 here, done. I am done with P2. Next priority is given to process P5, that is P5 is executed for 5 milliseconds. So it is 6 over here. And the next one is P1, which is having the priority value of 3. What is the burst time here? It is 10. So it is executed 10 seconds and the completed at 16 millisecond. Next is P3, which is having only 2 burst time. So it is 18. And the last is your P4. What is the value? It is having only 1 millisecond of burst time. So it is completed at 90 milliseconds. So this is the giant chart. So once you are perfect with this, you can easily identify these values. So the completion value of these process are, that is P1 has completed at 16, P2 at 1, P3 at 18, P4 at 19, and P5 at 6. And here, what is the formula for turnaround time? That is completion time minus arrival time, and with waiting time it is turnaround time minus burst time. So as you know that in the problem statement they have given that all the process has arrived at 0th second. So the value of the turnaround time is as same as your completion time. So 16, 1, 18, 19 and 6. But the waiting time will vary because the burst time need to be considered. So 16 minus 10, 6, 1 minus 1, 0, 18 minus 2, 16, and 19 minus 1, it is 18, and the last one is 6 minus 5, 1. So what is the average turnaround time? That is 16 plus 1 plus 18 plus 19 plus 6 divided by 5. You will get 12 millisecond. That is the average turnaround time. What about the average waiting time? It is 6 plus 0 plus 16 plus 18 plus 1 divided by 5. That is 41 divided by 5. It is 8.2 millisecond. This is how we calculate the average turnaround time and waiting time using priority scheduling. Smaller the priority value, highest the value that we need to consider. Let's see that how we solve. So in this example, we'll consider the 5 process and the length of this CPU burst time, which is given in millisecond. And what you need to do, you need to draw the Gantt chart illustrating the execution of these process using, remember this one, non-preemptive priority scheduling. So here it is mentioned clearly that you need to solve using non-preemptive priority scheduling, and you need to identify the turnaround time of each process and also waiting time for each process. But here it is not mentioned that the value of the priority of the process need to be considered. In the problem, you can see at 0th millisecond, 2 processes had arrived, that is P1 and P2, and the priority with P1 and P2 are 3 and 1. Now P2 is having higher priority than your P1. So what I do, I pick P2 and it is given to the CPU and it will execute completely because it is non-preemptive method. So it is having only 1 millisecond of burst time, so it is executed completely. So the next arrival process is at 3rd millisecond, means the CPU will be given to the process which are in the ready queue. So which process is in the ready queue? P1 is in the ready queue. So the CPU is given to P1 and it is executed completely. So 11. What is the burst time here? It is 10. The next one is, meanwhile P1 completes its execution, so it is completed at 11 millisecond. All other processes had arrived and they are waiting in the ready queue. So which are there? P3, P4 and P5. These 3 processes have arrived and they are waiting in the ready queue, and the priority values are 3, 4 and 2. Now you need to pick the higher priority process, that is P5 is having the higher priority. What is the burst time for P5? It is 5. So now the process is executed for 5 milliseconds. Now it is 16 here. The next priority is P3, which is having the burst time as 2. So 2, it is P3 and it is 18, and the last is the process P4, which is having the least of priority than any other process, and the burst time is only 1. So now it is completed at 90th millisecond. So this is the way how we draw the giant chart. What is the completion time here? P1 is 11, P2 is 1, P3 is 18, P4 it is 19, and P5 it is 16. And turnaround time is 11 minus 0, it is 11, 1 minus 0, it is 1. You know the formula, that is turnaround time, it is CT minus AT, and WT, that is waiting time, is turnaround time minus burst time. So the next P3 is 18 minus 3, 15, 19 minus 5, 14, and the last is 16 minus 10, it is 6. What is the waiting time, average waiting time, and average turnaround time of this process? We'll calculate that one. So the next one is waiting time, that is turnaround time minus burst time. 11 minus 10, 1, 1 minus 1, 0, 15 minus 2, 13, and 14 minus 1, 13, and the last is 6 minus 5 equals to 1. And here the average turnaround time will be 11 plus 1 plus 15 plus 14 plus 6 divided by 5. The value is 47 by 5 is equals to 9.4 millisecond. This is the average turnaround time. Now average waiting time, which is given as 1 plus 0 plus 13 plus 13 plus 1 divided by 5, and the value is 28 divided by 5, that is 5.6 millisecond. So this is the method to calculate the average waiting time and turnaround time using non-preemptive scheduling method. So kindly read the problem statement carefully. Here the problem is there are 4 processes and also the arrival time, burst time, and the priority is given. But the condition is consider the larger number as highest priority. Remember this one. The condition is given clearly, and also you need to calculate the average waiting time and the turnaround time, and need to draw the giant chart using preemptive priority scheduling. So we'll try to solve this problem. You can see here at the 0th second only one process has arrived, that is P1, and as you know that it is preemptive method that we need to consider by solving this problem, and also highest the priority value, higher the consideration. So your higher value will be higher priority. So this is the condition. So at 0th second the process P1 has arrived, no other process has arrived, so the process P1 will be considered for execution, and it is executed until the next process comes, and also it will check whether the currently executing process is having higher priority than the whatever the process has arrived. So it will execute for 3 seconds. Process P1, it is left with 7 milliseconds. So the next one is P2. At 3rd millisecond, 2 processes has arrived, that is P2 and P3. Among these two, P3 is having higher priority than P2. That is P3 is having higher priority than P2. What it does? The CPU will be given to the P3 because the priority is compared with the process which are in the ready queue, that is P1, P2, P3. Among these 3 processes, P3 is having the higher priority. So the CPU is given to the P3. So how many times it will execute? So it is executed for 2 time slots or 2 time units. because the next process will arrive at 50 millisecond. So assume that it is 5 here, so it is 2 millisecond, and again it is compared with the all other process which are in the ready queue. So now all 4 processes are in the ready queue. Among all the 4 process P3 is having the higher priority. So P3 is insisted to complete its entire execution. So the remaining time is with P3 is still 4 more seconds. So now P3 is completed at, remove this one, 6, and it is 9. So now it is done. What next is, now P3 is completed, P2 is having the burst time as 5, and P4 is having burst time as 3. Among these 3 processes, which is having the highest priority? The process P1. So now the process P1 is given a CPU and it is executed for remaining second. How many remaining seconds, milliseconds are there? 7 milliseconds. So 7 here, it is 16. Now the next priority, higher priority value is P4, which is having the burst time, P4 which is having the burst time as 3, and it is 19 here. And the last is P2, which is having the burst time as 5, and it is completed at 24 milliseconds. So this is how we draw the danger. What is the completion time for this process? That is 16, 24, 9 and 19. So what are the turnaround time? That is 16 minus 0, 16, 24 minus 3, 21, 9 minus 3, 6, and 14 minus 5, 19 minus 5, it is 14. So what are the average turnaround time? It is 57 divided by 4. So you will get 14.25 millisecond with respect to average turnaround time. Now let's consider for the waiting time. That is 16 minus 10. You know the formula, that is turnaround time minus burst time here. So the value is 6. 21 minus 5, it is 16. 6 minus 6, 0. And 14 minus 3, it is 11. So what are the average value here? That is 33 divided by 4. You will get 8.25 millisecond. So this is the way how we solve the preemptive priority scheduling. So this completes the priority scheduling algorithm. So let's see with the another algorithm in the next session. Thank you so much.